Hi, my name is Manish Gupta, and in this video, I'm going to talk about Muvera, which is multivector retrieval via fixed dimensional encodings. So let's get started. Let's sort of try to understand what is this thing called Muvera and how does it differ from Plaid. Okay. So of course, if you have not looked at my previous videos on multivector dense retrieval like ColBERT V2 and Plaid, please go over them before watching this video. Okay. So dense retrieval is basically doing retrieval using embeddings, and two types of dense retrieval have become popular these days: single vector dense retrieval and multi-vector dense retrieval. Single vector dense retrieval basically uses one vector embedding for query and one vector embedding for document, and then it basically works by computing maximum inner product similarity, so MIPS similarity. It's a dual encoder kind of a framework. It's fast, but not as effective. What is more popular these days is multivector dense retrieval, where essentially you have one embedding per token in the query as well as embeddings per token in the document. And popular methods include ColBERT, ColBERT V2, and Plaid. Right? The goodness about this is that it is more effective than single vector dense retrieval. However, multivector dense retrieval suffers from large index size and high latency. The similarity is computed by taking two sets of vectors, the first set being the query set and the other set being a document set or the passage set, right? And given these sets of vectors, because you have like one vector per token, right? So given these sets of vectors, you compute the similarity using what is called as max sim, or for every query token, you find the best matching document token, and you add up the similarities across all such matching query document tokens. Okay, so it's called maximum similarity or chamfer similarity, also called as relaxed Earth movers distance. Now, what Muvera does is the following. It basically is a multivector retrieval algorithm. So it sort of falls in the multivector dense retrieval domain. However, the way it works is by reducing this multivector similarity search to single vector similarity search. And again, the way it really does is by actually generating fixed dimensional encodings, also called as FDEs, of queries and documents. So queries and documents, as I mentioned, are multi-vector sets. So what it does is to basically really map these sets to basically fixed dimensional single vector encodings. So effectively, it sort of reduces multiple vector representations for a query to one vector. Similarly, it reduces multi-vector representation for a document to one vector, such that their inner product approaches multi-vector similarity, right? So that's that. So it's sort of try to approximate the multi-vector similarity using a single vector representation that is obtained in a specific manner, which I'll describe in the next slide. So hence, you can actually solve the multi-vector density problem using standard MIPS solvers. Now, the great part about Muvera is that they claim 10% improved recall with 90% lower latency on several BEIR datasets, BEIR benchmark datasets compared to Plaid. What you see on the lower part of the slide is the Plaid architecture versus the Muvera architecture. Of course, the Plaid architecture is something that I discussed in detail in the previous video. So it has like 4 different stages. The first stage of does candidate generation. The other 2 stages filter these candidates significantly. Candidate passages given a query. The last stage basically does a whole bunch of final ranking, much like ColBERT V2. Okay. However, since it basically does these 4 stages, it takes a whole bunch of time, and recall is limited in also thanks to basically these filtering steps. Okay. Muvera, on the other hand, basically is a very simple pipeline, essentially just 2 stages. The first stage essentially takes the query embeddings. Of course, I mean, in the offline, essentially, you take the document representations, you compute their ColBERT V2 embeddings. So basically, per token you have an embedding, and then you essentially use these you basically use Muvera to actually get fixed dimensional encodings. These fixed dimensional encodings are what you store for every document in a DISCAN index, DISCAN approximate nearest neighbor lookup index. When a query comes in, you essentially do the same thing. Essentially, you use the same kind of Muvera functionality to reduce these ColBERT V2 multi-vector embeddings to a single fixed dimensional encoding. And then you do a lookup on DISCAN index, get the candidate documents, top K candidate documents, and then you essentially do the proper chamfer re-ranking and return top K documents. And as I mentioned, what is observed is that this leads to 10% improved recall with 90% lower latency compared to Plaid. Okay. Now let's sort of try to understand how does Muvera work? How does this block work where basically you start with multiple vector representations, both for the query as well as for the passages. I'll use the word passages and documents interchangeably. So you can think about passages, documents, same thing. Okay. So how does basically Muvera really take these multi-vector representations of the query or multi-vector representations of the passages and map them to one vector, right? Such that maximum similarity multi-vector space is similar to the inner product based similarity in the single vector space. Okay, that's what this slide basically is all about. Okay, so let's start. So essentially, in multi-vector space, chamfer similarity is computed like this. Chamfer, or as it is also called as maximum similarity, you essentially have two sets of vectors, Q and P. Q stands for query. So it basically has, let's say if Q has like 10 tokens, so there will be like 10 vectors um, representing each, each vector representing a token, Qi in the query queue. Okay. Each vector is of the dimensionality d. So let's say it's basically dimensionality d. Similarly, for the passage, you basically may have like 1,000 passage tokens, and then each vector is basically of dimensionality d. For every query token, you basically try to find the best matching passage token, and then you compute this max similarity measure. Okay, that's also called as chamfer similarity measure. Okay. Now, the retrieval problem in the multivector space is basically this. You try to find the passage such that, if you really look at different tokens in the passage and you sort of compute the chamfer similarity between Q and BI, you essentially, you try to retrieve a passage, PI from the document set from the entire collection such that the chamfer similarity between the query and that passage is the highest, right? Now, let's basically also talk about what do you want to achieve from Muvera. So what Muvera wants to achieve is to basically take this set Q and then map it to just one single vector FQ of Q. Similarly, take this set of vectors P and map it to a single vector F doc of P, such that if you compute the dot product similarity, you essentially can approximate it with the chamfer similarity between the set of vectors Q and set of vectors P. Okay. Now, how does this FQ and F doc work is what we want to understand, right? So now basically for computing maximum similarity, in some ways, you are basically taking a particular token in Q and mapping it to a token in P, right? Basically the best matching token, so to say. And let's basically denote it by pi. So this is the function which sort of maps every token in Q to a best matching token in P. And if we knew pi, what we would do basically to compute this FQ and F doc is basically just concatenate all vectors Qi in Q and concatenate all corresponding vectors Pi in P, where P is the passage, P is the passage of the document, right? And then compute, and that gives you Q and small p, and then you just compute inner product. So that solves the problem, right? However, unfortunately, computing this mapping, which query token best matches with a passage token is the most time-consuming task. So therefore, you cannot really do this. So therefore, you cannot really do this. Okay, this is not practical. This is not practical. So let's see what is practical. What does Muvera do? Okay. So what Muvera does is basically take this d-dimensional space, and it basically partitions this d-dimensional multi-vector embedding space into B clusters. So it sort of divides them into B partitions or clusters. Okay, using this function, represented using this small psi. Okay. Now, this partitioning can be done using various methods. It could be done using locality-sensitive hashing or k-means. Both of them are pretty efficient in that senses. Particularly in their work, they found locality-sensitive hashing to give better results. Of course, locality-sensitive hashing depends on hashes and how many similarity hashes do you use. And the larger the number of similarity hashes you use, the better clusters that you get, and so on. Okay. So but you can partition the space into these buckets or partitions, as you can call them. So essentially, the d-dimensional space can be divided into B different partitions. Okay. Now, when you essentially now take any of the query token Q and any of that passage token P, you would observe that if Q and P essentially if they are essentially close to each other, if this passage token is very similar to this query token, they would rather be in the same cluster, right? They would belong to the same cluster. So therefore, this maximum similarity can actually be approximated in this manner. You would just go over the entire set of buckets, B buckets, and within each bucket, you would basically try to, for every query queue, you would basically just try to figure out for every query queue where essentially you have, the bucket is essentially K for that query queue, you would essentially find all those P's which are in that bucket and map it to essentially that particular passage token, which also belongs to the same bucket, right? So that's that. Now, this kind of works when there is only one passage token that collides or that falls in the same bucket as the query token queue. Unfortunately, that is not the case. And because when you're doing LSH, you can never guarantee that there will be only one passage token which will fall in that same query token. So therefore, they try to solve the problem by actually doing the following. They take all the query tokens that fall in that bucket K, right? And they compute the average, and they compute basically just the sum over all of those query tokens, right? So for all the query tokens, because you have to do max sim, right? So essentially what you do is to basically sum up all those query tokens, and you have to basically sum up, right? So that is why they sum up over all the query tokens which belong to the bucket Q, and that gives you your QK, okay? This is basically like a query representation for that particular bucket K, okay? And similarly, you do for P. For P, you don't sum, you basically compute average. So what you do is to essentially take all those P's which fall in the same bucket K, and then you do the average. This is the average essentially, okay? So, of course, it's written in a weird manner, but the point is it's basically just taking the average of the centroid of all those P passage tokens that essentially fall in the same bucket, okay? And then what do you do? So you basically just compute. Essentially, this boils down to if you basically take these QKs and you take these PKs, you concatenate them across all the buckets. That gives you a vector of size dB. What is D? D is the dimensionality of the original space, right? And B is the number of buckets. B is the number of buckets. So D is the dimensionality. B is the number of buckets. You concatenate all of those D-dimensional vectors, all of those B vectors, which are each D dimensions. So basically you end up with a Q bar and a the vector Q and vector P, which is a concatenation of these B vectors, each of dimensionality D. Okay. And then you do basically the dot product. And essentially, it's very easy to show that this is exactly approximating, or this is basically approximating the chamfer similarity. Okay. Now, the only problem is that this is a very large vector, dB in size, right? So therefore, what you can do is to basically just project it down. So, and the way you project down is by projecting each of those D-dimensional vectors into dproj. Now, dproj can be much, much smaller than capital D, than the dimensionality D. And the projection is basically, the projection can be learned in this manner, or rather can be computed in this manner. It is 1 over square root of dproj into S into X, where what is S? Well, S is a very simple thing. S is just a random matrix filled with ones or zeros. Okay, it's ones or minus ones, right? So it's uniformly distributed with plus or minus one entries. That's all S is all about. Okay, it's a random matrix, really. Okay, that's all. Okay, and it's not like weight, so it's not like trained or updated and so on. It's basically just a random matrix. Now, of course, one random matrix is not a great idea. And therefore, what they do is to basically repeat this entire process sometimes, so R reps times, okay, where they have their own size, okay. So remember, what are size? Size are basically clusters, which are basically obtained using LSH or k-means, right? So they have their own size and they have their own, projection methods, okay. Now that basically ends up giving you, B multiplied by D proj multiplied by R reps sized vector. So essentially, if you concatenate all of the vectors that you obtain across these R reps times, essentially what you get is an overall fixed dimensional encoding, which is B, number of buckets or number of clusters, so to say, right? D pros, the projected dimension, and R reps, how many times you repeat, how many times you compute these representations, right? So the final, so that's basically the D FDE. Now, of course, if you're really not happy with the large size that still this could be, you can actually project it back again with a random plus or minus one matrix, right? A random such projection matrix to any dimensionality that you really want to achieve at the end, any dimensionality that you want to achieve at the end. Okay. So there's a whole bunch of random projections that are involved, and Muvera is actually all about really taking those multivector representations and doing awesome random projections by using clustering-based concept as well, clustering being done here using LSH to obtain single dimensional representations, a single vector representations, and then just compute dot products. Okay. So this is how Muvera works, right? So essentially, if you were doing LSH and you divided the entire space into 6 different clusters, there are these blue ones, which are document embeddings, and orange ones, which are query embeddings. You can actually compute or estimate the chamfer similarity in this multi-vector space by actually just doing cosine similarity between these two fixed dimensional encodings computed using Muvera. Okay. So how does Muvera perform? So they basically try to experiment with 6 different data sets, as you see them here. These data sets differ in terms of number of queries and the corpus size, number of documents, and also the size of these documents, each of the documents, right? So there are large documents with like 165 tokens and small documents with just 18 tokens as well. Okay. So what they figure out first, of course, I'm just showing you results on 2 data sets, MS Marco and Hotpot QA. So what they figure out, so what do these charts show? These charts show, um, you know, so let's say if you were doing a full brute force chamfer similarity computation, and you basically obtained 500 candidate documents, right? Versus you did Muvera based similarity computation like this, using maximum inner product similarity computed on fixed dimensional encodings from Muvera, right? So what is the recall that you can obtain? Okay, so that's what it shows. So for example, and by the way, there are these multiple curves, and each of these curves stand for the FD dimension. So what is the overall FD dimension? So the awesome, takeaway from this, for example, on MS Marco, you can observe that Muvera achieves about 95% recall, while retrieving only 75 candidates. Just with 75 candidates, you can actually achieve 95% recall. If you are using, let's say the green curve, you are using 5120 dimensional embeddings. Okay. So it can actually learn these nice 5,000 sized, 5,000 dimensional embeddings such that just use 75 candidates and here you are done, right? You basically get like 95% recall compared to what brute force chamfer similarity would give you. Brute force ColBERT V2 could give you. Okay. They also compare their method on several data sets, as you can see here, with Plaid. And what you can observe is that typically the green one, which is Muvera, has lower latency compared to Plaid, and higher recall at K. I mean, this is end-to-end recall, so essentially getting the right documents, essentially, right? So it has much higher recall compared to Plaid. Muvera has higher recall compared to Plaid and lower latency. Okay. So in short, Muvera is multivector retrieval algorithm. It works by reducing multivector similarity search to single vector similarity search. And the way they achieve this is by generating fixed dimensional encodings of queries and documents whose inner product sort of approaches or approximates, multivector similarity. Thus, Muvera can, using this method, essentially Muvera can solve multivector dense retrieval using standard MIPS solvers. Experiments basically on BEIR datasets show that they can obtain 10% improved recall with 90% lower latency compared to Plaid. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.